So the one item was left for the other chapter, and that was reversible reactions. So I'm going to just do this once quickly, and then we go to next chapter. Okay. So reversible reactions. So assume that we have like A gives B and the return. So the very easy equation that the rate net, when we say rate, is the rate of forward and backward reactions together, would be rate forward plus rate backward or reverse. So this negative is implicit in the rate. So for example, if you write the rate for A, which we usually do for the limiting reactant, so there is a negative is implicit there because rate A is consumed. And when you go from B to A, obviously A is produced, so it's going to be positive, negative in a sense. You know what I mean? So the one negative going the forward reaction is implicit over here in rate forward. So, and always at equilibrium, that's the common questions that we ask. At equilibrium, what is zero? The rate net is almost zero. When we say almost, obviously when it gets 100% equilibrium is exactly zero, but we might not get to that final or complete equilibrium states. But in any events, to calculate the K, you need to equal to this rate to be zero. So just a quick example. Always I love examples because I can emphasize the points through the examples. So the question is, write the rate law for the elementary reaction. A gives a 2B, and obviously we have K forward A and K reverse A from the right to left. So if you write the reaction, so basically it would be like A gives 2B, and the reverse reaction is 2B gives you A. So we're going to write the rate reactions minus RAF is K forward reaction A CA and R reverse for A would be a K RA CB squared, because they are elementary, they follow the stoichiometry. So minus RA is K forward A CA minus K reverse CB squared. So if you factor the K forward, would be minus RA is K forward A CA minus CB squared KF KRA. What did we call this term? What is the K forward divided by K reverse? We called it KC, which has to do with the equilibrium, right? Capital K, your book shows as a capital K. So would be K forward, A, CA minus CB squared divided by capital K, C, which is the equilibrium rate. So at equilibrium, so your rate, the rate net is 0. And therefore, your CA minus CB squared over KC is 0. And obviously, we can easily calculate KC from this equation. CBE squared divided by CAE. The typical type of questions that we might encounter in chapter 3. So just give you some information about the reaction, and then considering the elementary type of reactions, calculate this, or Arrhenius type equations that you need to calculate the activation energy and the exponential factor. These are the typical questions that you might get. Any questions? Okay, so I'm going to just start chapter 4, which has to do with the stoichiometry. If you don't again recall that 5 Legos that we defined for this course, we started with the first bottom. At the bottom was the whole balance, which was the design equation, and then was the rate law. Which is the second Lego from the bottom, and then the third one is the stoichiometry. So, and your book, this Fogler book, has done a great job compared to all the reaction books explaining the stoichiometry. In very simple expression, few words, what the stoichiometry is that. You're going to just make a table from all the reactants and products, and try to find the relationship between those. And the objective is just to find the conversion versus the rate law. Because in the third chapter, your kinetics law is a function of concentration, correct? You say like minus RA is K times CA, or K times CA squared. So what you are doing in this chapter, you're going to just introduce the conversion that we already did, so the definition, and then you find the relationship of all the concentrations versus that conversion. Okay? So at the end of the day, so your rate law would be a function of conversion. This is what the stoichiometry is. Make a table. And then very easy. I mean, at the beginning you might say, oh, it's a very tedious job, but you make the table. So this is A, B, C, D. So A is consumed, B is consumed, C is produced, D is produced. And then how much is produced? Then you add them together. How much is all is consumed and how much is produced? And then that would be the relationship to conversion. And then we will be able to write the relationship between the rate law and conversion. That's what we do in this chapter. So if you approach it strategically, so it won't be any problem. So as I said, you have to just do some practice just to get your tables done, and that will be the main objective of what we are doing. So during this exercise, we are going to define some additional parameters like theta, delta, or epsilon that when it comes there, I will show why we are doing this one. And mainly is used for gases, because the gases are compressible, so we have to show how we can apply this relationship to each other. Okay, so did you see what's the objective for chapter 4? Okay, so I'm going to just, as usual, I'm going to start with some definitions. Okay, so chapter 4 is stoichiometry. Okay, so the block 1. So what I mean of the block 1, if you remember, this is block 1. So we did mole balance. Mole balance. So we needed the design equation for PFR, PBR, CSTR, batch reactor. We did that one and tabulated in the table, so easy to be used. So block 2. Block 2 was rate law. Right? This chapter has to do with block 3. Block 3, which is stoichiometry. So what we do in these chapters, we are going to just have the stoichiometry table. We're going to have a definition of concentration. Definition of concentration, and obviously conversion, and calculate equilibrium conversion. And calculate equilibrium conversion. That's what already we did in this chapter, but we are gonna look at it from conversion point of view. Okay. So in reaction engineering, conversion is important because always you mentioned. So we have some data about how much the reaction goes forward. These are the data or design data that you use for designing your plant and obviously the reactions. So we had, when we talked about the rate law in chapter 3, we came up with, as I mentioned, is a relationship between rate and the concentration, G of CIs. CI means the concentration of the reactants in the reactions, right? We had a expression. So most of the time, especially for homogeneous type reactions, we use the power law, right? So power law, so A to A, B to B, and so on and so forth. Then the stoichiometry. So is CI is H of X. So then we combine these two. We say that we are going to find minus RA as a function of conversion. So basically, using the stoichiometry table, we are going to find the relationship between reaction rate and the conversion. this is, I'm writing the main objective of the chapter 4, that at least you know where we are heading and what we want to achieve. Okay, so what is a stoichiometry table? Stoichiometry table. The table, a stoichiometry table, is a table that allows us to establish the relationship between concentration of reactants and products and conversion. So a table that allows us to establish the relationship between concentration of reactants and products and conversion. So basically shows the relationship between those, how does it work in a global approach between all of these reactants and products. So if you remember, let's consider a simple reaction. Again, we say A plus BA B gives CaC plus DAD. Let's just have a typical reactions that we have considered for this in rate law chapter 2 and chapter 3. So I'm going to just write, start with this, we consider this one to be the limiting reactant. I'm gonna use A, B, C, and D and show how much of A is consumed, and then how much of B is consumed, and then how much of C is produced, and how much of D is produced in the table. And then I add them together, and you will see how does the table works for you can apply these ones to calculation of the conversion and rate law. Okay, just again, we are going to do this one for a batch reactor. So assume a batch reactor. I'm going to just do these ones in the next lecture for the flow reactor. It's very similar, but for batch and flow, for batch reactor, I'm always using the moles, right? We have a certain amount of the moles of A, and then moles of B and C and D that are consumed or produced. For flow, this N is converted to F. We say FA, FB, FC, and FD. So it's very similar, but we just follow the routine that we did in previous chapter. I start with the batch system, and then I will generalize it to the flow reactors. Correct? Okay, so just remind you of the conversion definition that I had before. So what was the conversion? X. How do you define the conversion for, what is conversion? Remember? What was it? So let's assume we have Na0, and then after a while, your Na0 becomes Na. So how much A is consumed is Na0 minus Na, right? And then divided by the total amount of N. So basically it's a percentage in a sense. what percentages of A is used. And we apply this ones to limiting reactant, right? Correct? So is Na0 minus Na, what of A is consumed, and divided by Na0. Well, you can do this one as Na0 minus Na0 times X. So for if you look at the stoichiometry of the reaction, for every mole of A, react, how much of B is getting reacted? So just look at this. For every single mole of A that you use, the stoichiometry shows that you have BA of B is consumed, CA of C is produced, and DA of D is produced. Okay? So this is what we are going to do for each of them. Okay? For every mole of A react, BA moles of B react. So if you convert these ones, what I said, what would be the definition of NB? NB would be NB0. So look at, I'm trying just to find something to this for NB and NC. So how much, keep in mind that I'm using the conversion of A. If it was conversion of B, it would have been NB0 minus NB0 times XP. But you don't want to have different conversion. It's very confusing. You want to have one conversion. That's the conversion of limiting reactant AA. So what would be the, if you using 1 mole of A, BA moles, so what would be the NB? Minus what? Minus BA N Na0 times X. Right? Because for each mole of A, BA mole of B is consumed. So that would be Na0 times NB0, Na0 if you factor the Na0, minus BAX. You can do this type of a relationship for C and D. For example, for C would be like NC0, if it's 0 obviously would be 0, plus CA-NA0X. For ND, again in your right hand side for product, would be ND0, and if ND0 is 0, would be 0 plus DA times Na0X, right? So this is very simple. So here I'm going to define a theta, a parameter, we call it theta. And I will put the index here depending on what theta I'm talking about. So if it's theta B, that would be NB0 over NA0. So we're going to use this theta in the table. So just keep in mind, don't get confused. So we are going to have similarly, what is the theta A? 1, very good. Theta B is NB0 over NA0. Theta C would be NC0 over NA0, theta D, the same thing. So we're going to use this one. Simply because if you factor out your NA0, you are going to end up with similar term over here. NB0 over NA0, NC0 over A0, and ND0 over NC0. So therefore, if you introduce this theta, your equation for NB, this equation, becomes NB would be NA0, right? Theta B minus BAX. So help me out for other ones, very similar. So for NA is this, for NB is this, for species C, species product. Okay, so NC is NC0. What? Plus or minus here? We are talking about this reaction. A plus BAD plus gives CAC plus DAD. These reactions. Talking about these reactions. So NC0, NC is NC0 plus or minus? Plus Ca Na0 times x, correct? So if you factor out the Na0, would be Na0 Nc would be Na0. Factor out Na0 would be Na0 divided by Nc0 divided by Na0 plus Cax. So let theta C be NC0 over Na0, and then this equation becomes Nc is Na0 times theta C plus Cax. So for D, similarly for D would be, just if I would write the final expression, would be ND would be Na0 theta D plus DAX. So now I'm kind of ready just to make up the table for you, the stoichiometry table. So we have A, B, C, D. We know how much of A and B and C and D at the beginning, how much is consumed and how much is left. Very, very easy. I mean, very easy. This is like a conservation of mass that you did in the second year your course. It's very easy. So I'm going to turn the page. Okay, so I'm going to make a table as so we're going to have different species here. And then, well, symbol. And then initial, and then change, and then remaining, or final value of every species. So we're going to start with species A. Again, keep in mind, A AA plus BB gives CC plus BD. That's the equation. So A, well, the symbol is A. So initially we had, let's assume we have NA0 of A, and A acts as a limiting reactant. How much we are going to use? How much NA is used if assume X is the conversion? So it's minus NA0 times X, correct? We have initial value of NA0. NA0X is consumed. And how much is left? NA0 times 1 minus X. Everybody agrees with this? Right? So let's do with the same things with the B. So you help me out just to write down the B. In fact, you take the initiative. So B, let's assume we have the NB0 how much of B is used? Again, just to keep in mind, just write, if you want to write everything with respect to the NA0 would be NA0 times theta B. So how much we have used of, again, is negative because it's a reactant. BA NA0X. So how much is remaining? Is NA0 times theta B minus BAX. Okay, so next is C. So what would be the initial of C? So NC0 would be, again, just converted based on the definition of theta C, would be NA0 times theta C. And theta C definition, I'll put it here. Theta C is NSN C0 over NA0. Theta B was NB0 over NA0. Okay, so how much of the change we have for C is produced Ca Na0X because it's the product. So it's Ca, again positive, is Ca Na0X, and obviously the result would be Nc is equal Na0 times theta C plus Cax. The last one is D. So is ND0. ND0 is equal to Na0 times theta D, where theta D is ND0 over Na0. The change would be plus dA Na0 Na0X, and then the ND would be Na0 theta D plus dAX. So in a lot of occasions, we have, even for this 4-component A, B, C, D, you have something, we call it inert, is I. So it means that is in the vessel, is in your reactor, but doesn't get entered to the reaction. So you will see that you have to very carefully take care of this I. What this I does, it changes the mole fraction. So you need to take into consideration, although it's not attending or taking part in the reactions. Okay. So I will write that one is inert. Most of the time we show it as I. So like this one's N I0 would be N times theta I. And what is the change? 0. And we have the same. Na would be Na0 times theta I. Theta I, just a definition similar to other one, would be Ni0 over Na0. If you sum them up, the initial and changes, if you sum this one up, all these things together, so you're going to just call this one's summation of all these reactants and products and inerts. We call it NT0, N total 0, and then your total would be NT0 delta. I'm going to just talk about delta in a moment. Na0x. So what do you think delta is? Can you just guess from this this delta? What's that? Yeah, very good. So any other suggestion? So what delta is gives you some idea of the coefficient of the products minus coefficient of reactants. Because you have all of those there. You see you have 1, BA, CA, and BA. So that's delta. Delta shows change of the number of moles between the products and reactants. So if you put it in a mathematical expression, so delta is BA plus CA minus BA minus 1. And again, I will write down the theta I. So and theta I and different theta, we see the definition over here. I'm going to just, at the end of this chapter, I'm going to just give you this table, which is the same as I drive to the page a few minutes ago. So you're going to have this table and then all the exams, so you can like have it in front of you. So you don't have to memorize it. Although you need to know how to get this table out. So sometimes when you have the numbers change, that coefficients change, so that theta and this delta gets problematics for the students when they want to make up this table. But this is the table. I'm going to just give it as a single page at the end of this chapter. You have it in all the quiz and exams. Any questions about? Because it's a simple concept. It's not difficult. But as I said, you are dealing with different substances. So then write it down, and sometimes you might just miss it, negative or positive sometimes, and then your total comes wrong here. Otherwise, the concept is easy. So this is what the stoichiometry is, right? So you're going to practice more and more just to show you how, now you have this one, you're going to just see how you're going to connect this one to the conversion and to the reactions, right? And then another important concept comes to play, and that's the difference between gases and liquids. This is very important. You know what? The main difference, I mean, aside from the definition that you had from 201, is just the volume change. So if your system, if you're in your system, you have a constant volume, which is for liquids. And also some gases might have a constant volume. Don't change the volume. When it's going to be? When the number of moles of the reactants and products are the same. Ideally, each mole has 22 point, how much? 4? I forgot from the chemistry leader. So if you have the same number of molecules from the products and reactants, there won't be any volume change, which makes your life much easier as opposed to when you have a volume change.